In the coldest outskirts of our planetary story, far beyond the orbits we are taught to picture in school, a single point of light has begun to misbehave. It is catalogued with a long, careful name, Bernardinelli-Bernstein, a comet so large that even cautious estimates put it at well over 100 kilometers across, a chunk of primordial ice the size of a small country that should have slept quietly in the Oort cloud for billions of years. Yet in the last 72 hours, if you follow the right feeds and listen to the right late-night voices, you can feel our cosmic narrative splitting in two. Some of those voices are suddenly telling you to forget 3I Atlas, to stop asking about its strange new acceleration, and to turn instead toward this newly awakened giant that is now drifting inward toward a close pass in 2031. They insist that the real problem, the real threat, is this slow, heavy body that seems to be glowing before it has any right to, and that the story of 3I Atlas is a distraction we should let fade. If you open an official bulletin, you will find soothing language. Bernardinelli-Bernstein is described as a long-period comet, probably born in the distant Oort cloud, on a path that will bring it no closer than a safe distance beyond Saturn. You will see the numbers clustered neatly together, orbital period measured in millions of years, distance in tens of astronomical units, diameter estimated somewhere between 100 and 150 kilometers. You might see a passing reference to a thin veil of carbon monoxide gas already lifting off its surface while it is still far from the sun, framed as an interesting detail rather than a reason to worry. But in the quieter corners of the observing community, a few patient skywatchers point out that the brightness has not followed the usual script, that the timing of the outgassing looks early, and that the curve of its activity does not sit comfortably on top of the models designed for smaller, more ordinary comets. In those same spaces, another pattern is emerging. Whenever the name Bernardinelli-Bernstein appears, the name 3I Atlas is gently pushed to the side, downgraded from an unsolved puzzle to a closed case. A popular story has formed almost overnight. Bernardinelli-Bernstein is the new villain, the new focus, the new monster under the cosmic bed. 3I Atlas, with its unexplained change in acceleration, is quietly relabeled as a misunderstanding that diligent scientists have already resolved. On the surface, this looks like nothing more than the natural drift of attention, the way news cycles move from one headline to the next. Yet there is something strangely coordinated about how quickly it has happened, as if the narrative itself is being steered by an invisible hand that prefers these two objects to be thought of separately. Astronomers, to their credit, have offered normal explanations for Bernardinelli-Bernstein because that is what they are trained to do. Some invoke the slow pull of the Milky Way, the way galactic tides can gently reshuffle the Oort cloud over tens of millions of years. Others point to the ancient passage of a star, a distant visitor whose gravity could have perturbed a whole swarm of icy bodies and sent a few inward, with Bernardinelli-Bernstein simply the largest among them. More speculative voices bring back the shadow of a hypothetical Planet 9, a still unseen world whose gravity might be sculpting the outermost orbits in ways we have not yet fully measured. Each of these ideas has some weight. Each can be made to fit part of the picture. Yet when you look closely, none of them quite settles the matter. The numbers work on paper, but details have to be stretched. The scenario lines up in one place and slips quietly in another. That leftover mismatch is where the whispers begin. A handful of researchers, often speaking more freely in long, unedited interviews than they do in formal papers, admit that Bernardinelli-Bernstein does not behave exactly like the textbooks would suggest. Some point out that its early activity could imply unusual internal structure, pockets of volatile gas closer to the surface than expected, or fractures that open wider than our simulations assume. Others are willing to say, softly, that the simplest models might be missing a perturbation, a small additional influence that has not yet been identified. In a universe full of normal comets, having one outlier would not be surprising. What makes this one unsettling is the combination of its size, its timing, and the way it has arrived just as our collective attention is being guided away from the unresolved motion of 3I Atlas. Because while this giant is being framed as the main act, 3I Atlas has quietly become the thing we are supposed to forget. For months, questions about the strange new acceleration of 3I Atlas sparked debates about non-gravitational forces, outgassing, and the thin line between natural and artificial behavior. Then, almost on cue, as Bernardinelli-Bernstein rose in the public imagination, those questions were gently folded away. Official statements began to sound more certain. Coverage shifted, threads were closed or redirected. In the span of only a few dozen orbits of Earth, the conversation pivoted from one enigma to another, with very little overlap allowed between them. It is in that gap, between what is discussed and what is discouraged, that a different kind of story can begin. Imagine for a moment that Bernardinelli-Bernstein is exactly what the data say it is, a vast and ancient comet on a long looping path that happens to bring it into the outer reaches of our planetary system in the early decades of this century. Imagine also that 3I Atlas is exactly what its trajectory suggests, an interstellar visitor with a phase of acceleration that does not quite fit known physics. Is it really so unreasonable to ask whether the timing of these two events might be more than coincidence? Is it really so strange to wonder whether a giant piece of ancient ice and a nimble accelerating object could be part of the same larger pattern? Here, as always on this channel, our role is not to shout answers, but to walk carefully through the questions, keeping one eye on the hard science and one eye on the spaces where data thins out and imagination must carry some of the weight. We will move slowly through brightness curves and orbital diagrams, through old survey images and new tracking solutions, tracing how Bernardinelli-Bernstein has moved from obscurity to the center of the stage. We will listen to the official reassurances that its closest approach in 2031 will be safely distant, and we will set those reassurances next to the quiet acknowledgments that its behavior is not entirely routine. If you find comfort in that careful balance, in letting your mind drift between what is known and what might be hidden, you are in the right place. You can help this journey continue by subscribing to the channel, by letting these stories play softly as you fall asleep, and by sharing your own thoughts in the comments about what you think Bernardinelli-Bernstein and 3I Atlas really are. The more quietly curious minds we gather here, the easier it becomes to explore ideas that do not fit neatly into headlines. Now, dim the lights. As darkness settles around you, picture Bernardinelli-Bernstein as more than a point of light on a chart. See it as a slow-turning mountain of ice and rock, its surface laced with buried seams of frozen gas, beginning to sweat and glow in the thin sunlight that reaches it from impossibly far away. Around it, the Oort cloud is not just a theoretical shell, but a vast, sparse halo of countless other bodies, most of them content to sleep. Only this one has started to stir, like a sleeper rolling over in bed after hearing a distant sound, and in the background of that movement, somewhere much closer to the sun, the unresolved path of 3I Atlas continues to bend in ways we do not fully understand. For tonight, it is enough to hold that image and that question together. A colossal comet that has slept since before our planet formed is now turning slowly toward the sun, while another visitor, 3I Atlas, refuses to behave quite like a natural rock. In the quiet between these two, we will look next at what happens when Bernardinelli-Bernstein reaches its closest approach in 2031, and why some of its so-called normal behavior looks less reassuring when examined up close. By the time Bernardinelli-Bernstein sweeps through its closest approach to the Sun in the early 2030s, official reports suggest it will do so quietly, far beyond Saturn, a distant event that barely touches human life at all. When you read those reports carefully, you find a neat, almost reassuring narrative. Bernardinelli-Bernstein was first seen in archival data from a deep survey, then recognized years later as an enormous comet with a diameter likely above 100 kilometers, following a stretched-out orbit that takes millions of years to complete. Its perihelion, the point where it comes closest to the Sun, sits around 11 astronomical units, comfortably outside the orbit of Saturn. At that distance, sunlight is weak, solar wind is thin, and this journey is supposed to be a graceful, uneventful swing through the outer suburbs of our system. In the simple version, Bernardinelli-Bernstein is a curiosity rather than a crisis. We are told that it will never cross the orbits of the giant planets, that its path has been solved, and that its bulk will remain a cold, indifferent presence far from Earth. The orbit diagrams shown in public briefings are tidy and color-coded, with Bernardinelli-Bernstein sketched as a pale loop that dips inward toward Saturn's domain and then retreats, a slow visitor that merely passes by. If you stop there, the date 2031 becomes nothing more than an interesting entry in a celestial calendar, another distant alignment to add to a long list. Yet this giant has already refused to stay within the simple version. Long before it should have, Bernardinelli-Bernstein began to glow. Telescopes picked up a faint coma and hints of a tail, while it was still so far from the Sun that most comets would remain frozen and dark. Spectra suggested carbon monoxide gas lifting off its surface, an invisible wind of molecules escaping from buried reservoirs that were somehow waking up in the deep cold. The distance involved is not a poetic exaggeration. We are talking about tens of astronomical units, where sunlight is weakened to a small fraction of the strength it has near Earth. According to the standard models, very few things should be happening out there. To explain this early activity, researchers returned to their equations. They adjusted assumptions about how porous the surface of Bernardinelli-Bernstein might be, how fractured the crust, how shallow the volatile layers. It is possible, they suggest, that this comet is built like a sponge, with pockets of gas and dust closer to the surface than average, ready to vent as soon as the slightest heat arrives. Others propose that past encounters may have already warmed parts of its interior, leaving fossil heat that leaks out slowly over time. These ideas are not wild. They sit within the range of respectable comet physics. But each relies on details we cannot yet see, and the fit between model and measurement is still looser than most people realize. The orbit itself, too, carries quiet complexities. On paper, it is a long, smooth ellipse, dominated by the gravity of the Sun. The gravitational influences of the giant planets introduce only small corrections, and in many public discussions, those corrections are treated as negligible. Yet tiny forces have long memories in celestial mechanics. A small asymmetry in outgassing, a subtle push from a jet of carbon monoxide on one side of Bernardinelli-Bernstein can ever so slightly shift its trajectory over years and decades. For small comets, this is a familiar story. For an object this large, it should be much harder. The very mass that makes Bernardinelli-Bernstein impressive should also make it resistant to such nudges. That is why the combination of its size, its early activity, and its long approach to perihelion draws the attention of those who like to read between the lines. When a system is this delicately balanced, a slow, continuous push can matter more than a sudden shove. Imagine a heavy door that should stay still, yet over the course of an evening, you notice it has drifted a few centimeters open. No single gust of wind explains it. Instead, it feels as though some quiet, persistent pressure has been at work, something that does not show up in the simple description of the room. Bernardinelli-Bernstein carries that same faint unease. Its official orbit is tidy, but in the background, each episode of outgassing is like one more small hand pressed against the door. In interviews, some astronomers acknowledge this in cautious language. They speak of non-gravitational parameters that are not yet firmly pinned down, of light curves that show hints of irregular behavior, of future refinements that will update the predicted position of Bernardinelli-Bernstein around the time of its 2031 swing. None of this means that disaster is looming. It does mean that the true path of this comet is still a living calculation, not a finished one, and that the phrase safe distance hides a lot of quiet, ongoing work. The map we carry in our minds, with clean lines and fixed dates, is a simplification laid over a more fluid reality. There is another layer that rarely enters the public summary. To speak openly about how subtle forces can bend an orbit is to invite questions about what might supply those forces. Standard answers are reasonable: uneven sublimation, internal structure, previous passages through the inner system. But once you accept that a comet's path can be reshaped by gentle, persistent influences, it becomes harder to dismiss the idea that unseen interactions, or even encounters with other bodies, could accumulate over time. You do not need to jump straight to artifices or engines to feel the edge of that possibility. You only need to recognize that the line between a purely gravitational orbit and a guided one can be very thin from a distance. Viewed from far away, a plotted trajectory tells you where Bernardinelli-Bernstein is expected to be in 2031. It does not tell you what it will have experienced on the way. It does not tell you whether small, compounding pushes will have shifted its schedule or slightly altered the geometry of its closest approach. When people speak of 2031 as if it were carved in stone, they are really speaking about a forecast built on current data and best guesses about the physical behavior of an unusual comet. The truth is softer, more provisional. Out beyond the orbit of Uranus, Bernardinelli-Bernstein is still in the process of becoming whatever it will be when it glides past Saturn's distance. As you drift toward sleep, you might imagine that future moment not as a sharp point on a calendar, but as a broad, hazy window in time and space, with a giant comet entering it along a path that can still be imperceptibly tuned. If something or someone wanted Bernardinelli-Bernstein to arrive in a slightly different posture, a slightly different phase of rotation or outgassing, there would still be years to make those changes nearly invisible from our point of view. In the next part of our story, we will look at the forces we know about, the tides and distant stars, and hypothetical planets that might have nudged this giant awake, and we will ask whether they are enough to account for its strange, early stirring. If you ask out loud, what could possibly have pushed Bernardinelli-Bernstein out of its ancient sleep, the first answers that come back sound solid and scientific. They speak of tides, passing stars, and hidden planets, great slow forces that have been quietly combing through the Oort cloud since long before any human looked up at the sky with questions. On paper, each of these explanations has a certain grace. They fit comfortably into diagrams and lectures. They let us imagine Bernardinelli-Bernstein as a passive passenger in a story written entirely by gravity. Yet if you stay with the details for more than a few calm minutes, the elegance begins to fray, and what seemed like a finished answer starts to look more like a sketch over something still unknown. The galactic tide is the most patient of these suspects. Our solar system does not sit alone in space. It orbits the center of the Milky Way, moving through the faint density waves of the galactic disk. Over tens or hundreds of millions of years, the collective gravity of that disk gently tugs on the distant Oort cloud, stretching and squeezing it like a diffuse halo of dust. In simulations, that tide can indeed send a slow rain of comets inward, one here, one there, a statistical drizzle of icy fragments making the long fall toward the sun. It is a beautiful idea, and in many cases it works. But galactic tides are broad and indifferent. They do not single out one comet the size of a small country and whisper that now, specifically now, is the time to wake. If Bernardinelli-Bernstein were just one member of a larger wave of comets arriving together, this explanation would feel cleaner. Instead, we are left with a solitary giant whose timing is, at best, an interesting coincidence. The passing star scenario offers a different picture. Every so often, another star swings through the outskirts of our solar system, its gravity brushing the Oort cloud and jostling bodies that have slept since the earliest days of planetary formation. Astronomers have identified real candidates for such encounters, like a dim red star that seems to have passed within a light year of the Sun a few million years ago. It is easy to imagine that event sending a spray of comets inward, including something as massive as Bernardinelli-Bernstein. Yet when people try to line up known stellar flybys with the orbit of Bernardinelli-Bernstein, the match is not clean. The distances, timings, and directions can be made to approximate the needed push, but only by stretching uncertainties and choosing parameters at the edge of their ranges. Again, the story becomes possible, but not comfortably precise. Then there is the shadow of a world we have never seen, the hypothetical Planet 9. According to the idea, an unseen planet far beyond Neptune could be sculpting the orbits of remote objects, herding them into strange alignments. If such a planet exists, it is tempting to imagine its gravity also nudging Bernardinelli-Bernstein, bending its immense orbit so that this particular perihelion happens to fall in the early 21st century. Models have been built where this works, where the right mass in the right place can coax a giant comet into the inner outskirts of our system. But invisible planets have to answer to visible data. Surveys that would have revealed many versions of Planet 9 have not yet seen it, and to keep the hypothesis alive, theorists are forced to move it to more elusive orbits. The more elusive it becomes, the harder it is to make it do exactly what Bernardinelli-Bernstein seems to have done. When you set these explanations side by side, a pattern appears. Each can be tuned to be roughly compatible with the existence of Bernardinelli-Bernstein on its present path. None slips into place with the satisfying click of inevitability. Galactic tides provide a background rain, but not the sense of a single, deliberate awakening. Passing stars can stir the cloud, but the known candidates require generous error bars to land their influence on this one comet at this exact epoch. A hidden planet can be invoked, yet it must be both powerful enough to sculpt distant orbits and shy enough to evade detection. What remains is the feeling that our equations are being asked to do just a little more work than they comfortably can, as if there is a missing term that no one is quite ready to name. That missing term does not have to be exotic. There are subtle forces we know about, but have not fully mapped for an object this large. A comet does not merely fall, it breathes. Every jet of gas that erupts from its surface carries away momentum. For smaller comets, these non-gravitational forces can significantly shift their paths over time, nudging them into slightly different orbits with each outburst. With Bernardinelli-Bernstein, the expectation was that its sheer mass would mute these effects, rendering its orbit almost purely gravitational. The early activity we have already seen complicates that assumption. If a comet the size of Bernardinelli-Bernstein can sustain uneven outgassing for years on its approach, the accumulated pushes could matter in ways our present models do not yet capture. Still, even that may not be enough. To reshape the path of such a massive body in a way that meaningfully changes its rendezvous with the outer solar system would require an almost choreographed pattern of vents and jets timed and oriented just so. That does not mean it is impossible. Nature is capable of intricate behavior. Fractures and rotating spin states can create repeating patterns of activity that add up to a larger effect. Yet the more we rely on that complexity to make the numbers work, the more we are describing a very particular sequence of events, one that just happens to steer Bernardinelli-Bernstein into a specific window of space and time. From there, the mind drifts toward less comfortable possibilities. If an unseen term is really needed to explain the full story, it could be something as mundane as a population of distant perturbers we have not cataloged, clumps of mass in the outer cloud that our surveys are too shallow to see. Or it could be a single interaction that left no obvious signature, a glancing exchange of momentum with a body that did not stay. The equations themselves do not care whether that body was a modest, dark fragment or something more deliberate. At our current distance, both would appear in the math as just one more small force, one more nudge layered on top of many others. For the most cautious thinkers, the discussion ends there. They are content to say that Bernardinelli-Bernstein reflects the limits of our data and our imagination, that with better measurements and deeper surveys, the remaining gaps in the story will close. Others, especially those who stay up late, staring at residual plots and unexplained flickers in light curves, are less certain. They note that while we are being asked to treat Bernardinelli-Bernstein as a self-contained puzzle with purely natural answers, another object, 3I Atlas, has shown a phase of acceleration that already forced us to contemplate unfamiliar forces at work. As you let your thoughts slow, you might picture the outer solar system not as an empty margin, but as a stage where many influences overlap, some mapped, some only suspected. A giant comet begins to stir before it should. Its orbit can be described but not perfectly justified. The usual suspects can be lined up but not cleanly convicted. Somewhere beyond the edge of the official diagrams is a blank space labeled with nothing more threatening than a question mark. In the next part, we will turn to 3I Atlas and its so-called exhaust, and we will ask whether the same missing term that haunts the story of Bernardinelli-Bernstein might also be whispering in the trajectory of this interstellar visitor. For 3 long chapters, we have kept Bernardinelli-Bernstein in the center of the frame, a slow-moving giant stirred from the deep. Now the camera drifts inward toward a much smaller point of light that behaves in a far less obedient way. 3I Atlas, the interstellar visitor with the unexplained change in its motion, is usually shown in simple orbital plots as a thin curve swept past the sun. But when you follow the trail of images, instead of the smooth line, you find something stranger. In a handful of processed frames, especially those pushed to high contrast and sharpened for drama, narrow plumes seem to leap away from 3I Atlas in the direction of the sun. Thin white blades against a dark background. To many late-night viewers, and to more than one rival channel, those plumes look exactly like rocket exhaust. The story almost writes itself. A dark craft, an improvised rocket, a vehicle gunning its engines as it threads the inner system. There is a certain satisfaction in that picture. It is simple. You point a nozzle away from where you want to go, you burn fuel, and you accelerate. When people overlay arrows on the images of 3I Atlas, aligning them with the apparent jets, it can feel as though the universe has kindly provided a diagram. Here is the body, here is the exhaust, here is the thrust line. Viewers circle the features and freeze frames, comparing them to familiar photographs of spacecraft plumes near Earth. And because the plumes in some frames seem to tilt sunward rather than away from the sun as a natural tail would, the temptation is to say that nature has been ruled out and a machine has been revealed. The difficulty begins when you ask the pictures to carry more weight than they were designed to bear. Cometary jets, even on ordinary bodies, are complex three-dimensional structures. They do not launch from a fixed nozzle, but from vents scattered across a rotating, irregular surface. What we see from Earth or from an orbiter is a projection of that messy geometry onto a flat detector. A jet that is physically directed away from the sun can, from the right viewing angle and at the right moment in the rotation, appear to lean toward it. A fan of outgassing from the night side of a nucleus can be backlit in a way that mimics a sunward plume. Long exposure times smear motion into smooth lines. Image processing designed to pull a faint object out of noise can exaggerate features that are barely real. All of these caveats are familiar to people who study comets for a living, but they are less familiar to casual viewers and to channels that need a crisp story. So the term exhaust catches on. It is not entirely wrong to use the word in a descriptive sense. Gas really is leaving 3I Atlas. Dust really is being pushed into a thin envelope by sunlight and solar wind. The problems appear when exhaust is used to mean rocket, when a naturally venting comet is rebranded as a jury-rigged spacecraft. The physics begins to object. The amount of mass that would have to be thrown out of a body like 3I Atlas to produce the observed change in acceleration using ordinary chemical propulsion is enormous. Calculations that assume simple rockets quickly run into a wall. Either the exhaust velocities must be unrealistically high, or the comet must have started with an implausible reservoir of propellant. At the same time, something stubborn remains. Even after you account for projection effects and image processing tricks, the behavior of the features near 3I Atlas is not entirely routine. Some analyses of its coma have suggested asymmetries that are hard to reconcile with simple sublimation from a random collection of vents. There are hints that the non-gravitational forces acting on 3I Atlas are aligned in a surprisingly coherent direction over long stretches of its path, rather than wandering as you might expect from chaotic outgassing. A few quiet papers speak of statistically significant residuals, small differences between predicted positions and measured ones that are best explained by a continuous directional push. If the rocket metaphor is crude, the idea of sustained thrust is harder to wave away. That is where the phrase exhaust illusion becomes useful. The illusion is not that there is no thrust at all. The illusion is that whatever is pushing 3I Atlas must resemble the rockets we build. Calling the plumes exhaust in that sense is like looking at a lightning storm and insisting it must be a bank of household light bulbs simply because both glow. The features in the images may be real, but the human instinct to map them onto familiar hardware may be leading us astray. If 3I Atlas is being accelerated by something more subtle than hot gas blasting out of a nozzle, then the thin, sunward pointing streaks near it could be side effects, not the engine itself. They might be visible tracers of a process that mostly hides in spectra and timing, a kind of scaffolding of light around a deeper mechanism. In that frame, a different kind of speculation opens. Suppose 3I Atlas carries or embodies a propulsion system that works not by throwing reaction mass violently away, but by manipulating fields, or by coupling to the medium of space in a way our current physics of finesse only hints at. Any real implementation of such a system would still have consequences. It might heat pockets of gas unevenly. It might channel charged particles along narrow paths. It might twist the local magnetic field so that dust and plasma collect in unnatural shapes. To a distant camera, those consequences could look like jets pointing in defiance of simple intuition. The rocket story would be wrong, but the intuition that something deliberate is happening would not be entirely misplaced. There is an imaginative leap here, and it is important to name it. Nothing in the existing data forces us to accept exotic propulsion. A sufficiently complicated pattern of natural outgassing, combined with rotation and fractured topography, could in principle produce a similar signature. Yet the same way we felt a missing term in the story of Bernardinelli-Bernstein, there is a missing ease in treating 3I Atlas as just another active comet. Its classification as an interstellar object, its unusual acceleration profile, and the persistent directionality of the non-gravitational forces combine into a shape that does not sit comfortably in any ordinary drawer. When people reach for the word exhaust, they are groping for a label that conveys that discomfort. As you listen to this, you do not need to decide which picture you prefer. You can simply hold both in your mind, letting them drift past each other the way two orbits cross in space. In one, 3I Atlas is a natural body, shedding material in patterns that happen to produce misleading images. In the other, 3I Atlas is a vehicle or tool, and the so-called exhaust is only the visible fringe of a deeper engine. Both are anchored to real measurements. Both can be made to touch the known laws of physics, though one stretches them more than the other. The unresolved space between them is where the quiet unease of this story lives. Somewhere inside that unease lies the reason certain institutions are comfortable letting the rocket narrative spread. A crude, improvised engine is easy to dismiss. It belongs to science fiction. It makes 3i Atlas feel like a story people tell themselves, not a phenomenon serious observers need to track. A more refined idea, in which the visible plumes are misleading clues to a sophisticated form of propulsion, is harder to talk about without inviting discomforting questions. If 3i Atlas is steering with precision that does not match any simple exhaust model, then we have to ask what path it is following and what rendezvous it might be shaping somewhere in the future. As you drift a little deeper into the quiet of the night, imagine 3i Atlas not as a rocket firing wildly in the dark, but as a gliding object wrapped in gauzy veils of gas and dust, its true engine hidden beneath the glow. The sunward plumes that so many thumbnails circle might be nothing more than lanterns on the surface of a much larger pattern, marking out where energy leaks into forms we can see. In the next part, we will set the rocket metaphor aside entirely and ask what it would mean to treat 3i Atlas as an engine from the start, an entity whose new acceleration is not a glitch but a signature, and we will follow that line of thought toward the place where its path begins to bend toward Bernardinelli-Bernstein. If you stay with 3i Atlas long enough, letting the noisy talk of rockets fade into the background, a different picture begins to form. In that quieter picture, 3i Atlas is not a desperate vehicle burning stored fuel, but something closer to a self-contained engine, an object whose shape, composition, and internal physics are all tuned for one purpose: to keep changing its path long after any ordinary comet would have surrendered to gravity alone. The first clues to this are not dramatic. They live in the small, persistent differences between where 3i Atlas was supposed to be and where telescopes actually found it, in the way its non-gravitational acceleration remained coherent over time, instead of wandering randomly. Simple exhaust would have told one kind of story. What we see instead hints at a system that is able to maintain a steady push, as if it were drawing power not from a tank, but from the environment itself. Engineers who run the numbers on a rocket interpretation reach a kind of quiet dead end. To account for the observed change in the motion of 3i Atlas with familiar propulsion, you have to imagine that a significant fraction of its total mass has been hurled away at high speed. Even if you give it optimistic exhaust velocities, the mass ratio becomes punishing. The more you try to fit the data into the rocket equation, the more implausible the starting conditions become. You end up with a comet that would have needed to be stuffed with propellant in a way that makes no physical sense, or with jets that run far hotter and faster than any known chemical or nuclear exhaust could explain, all while leaving behind only delicate plumes of gas and dust. It is not that the math is impossible, it is that it feels strained, as if reality is politely refusing to cooperate with our simplest story. There is another family of possibilities that sits a little closer to known physics, yet already feels more like an engine than a rocket. In this family, 3i Atlas is designed to interact with light and fields rather than just hurling mass away. A body with a carefully chosen shape and a surface tuned to reflect or absorb sunlight in asymmetric ways can experience a subtle but continuous thrust. Effects like radiation pressure and thermal emission can be harnessed, not just endured. For small asteroids, we call this the Yarkovsky effect, and treat it as an annoyance to be modeled. With 3i Atlas, imagine that kind of effect scaled up and sharpened, with panels or layers that can change their orientation to modulate the force. To distant observers, the result would look like a natural body, whose acceleration does not quite fit our standard templates, gaining speed or bending its path in ways we would struggle to explain with random jets alone. The so-called exhaust would then be less important than the way the entire surface of 3i Atlas is being used as a sail, a radiator, and a control system. From there, it is not a large step into the territory that people in official roles prefer not to name in public. If 3i Atlas is an engine in that broader sense, it may be exploiting not only light, but also magnetic fields and charged particles, channeling the very flow of the solar wind into directed thrust. We already know how to sketch primitive versions of such systems in our own textbooks. Electric sails that deflect ions, plasma thrusters that accelerate particles along magnetized paths. Extend those ideas by a few steps. Give them an interstellar civilization's head start, and you can picture an object that arrives looking like a comet, then quietly reconfigures its outer layers to couple to the medium around it. The visible jets would be only the froth at the edges of that process, pockets of heated gas and dust marking where energy leaks into familiar forms. The true engine would be written in lines of force and patterns of plasma too fine for our current instruments to resolve. In this light, the phrase new acceleration becomes something more precise. The change in the motion of 3i Atlas would not be a random outburst, but an activation event, the moment when passive coasting ends and active steering begins. Before that moment, 3i Atlas behaves like a stranger falling freely through our system. After it, the trajectory starts to show signs of preference, bending gradually toward a set of coordinates that have not yet been announced on any mission patch. The timing of that activation matters. It coincides not only with specific distances from the sun, where certain physical regimes change, but also with a period when our own surveys are finally sensitive enough to track both 3i Atlas and Bernardinelli-Bernstein with increasing precision. The engine, in other words, wakes fully only when both its own sensors and ours have enough information to work with. This is where the idea of the rocket becomes more than just wrong. It becomes useful misdirection. A crude exhaust story keeps attention focused on the most obvious features in the images, the bright streaks and overlapping plumes, while leaving the deeper pattern unexamined. If 3i Atlas is operating an engine that relies on orchestrated interactions with light and plasma, then the true signature would not be a dramatic flare in a single frame, but a slow, consistent trend in its non-gravitational parameters over months and years. Spotting that trend requires people to sit with residuals and long tables, not just thumbnails and headlines. It requires them to ask why the direction of the inferred thrust remains so stable and why it seems to adjust in ways that correspond less to random outgassing and more to a path being tuned. That kind of work is quieter, and it is easier to keep submerged beneath official language. As you let these ideas settle, it may help to picture 3i Atlas from inside rather than outside. Imagine that beneath the crust and coma is a skeleton of fields, a lattice of conductive channels and resonant cavities that can be reconfigured like muscles. When certain regions are activated, charged particles are drawn in, accelerated, and released along chosen directions, creating a net push that can be sustained without exhausting a stockpile of chemical propellant. From a great distance, all we see is a slight, persistent deviation from a ballistic path and a fuzz of light where material is stirred up. From within, 3i Atlas feels more like a living machine, flexing against the invisible currents of the solar wind. This is an imaginative leap, and it must be acknowledged as such, but it is anchored in real ideas our own scientists already play with on a smaller scale. If something like this engine is at work, then the next question is not whether 3i Atlas can steer, but what it is steering toward. Engines imply missions. Trajectory changes imply targets. Here, the story intersects again with Bernardinelli-Bernstein, the giant that is supposed to be treated as a separate problem. A body capable of adjusting its motion over many years using an embedded engine would be uniquely suited to intercepting slow, massive targets on distant orbits. It would not need to streak across the inner system in a blaze of obvious thrust. It would only need to keep applying gentle pressure year after year until its path and that of its chosen object begin to bend toward a shared point in space. For institutions that thrive on clear categories, this is an uncomfortable possibility. A rocket is something they know how to talk about. It belongs to familiar diagrams and treaties. An engine woven into the entire structure of an interstellar visitor, exploiting ambient fields in ways that verge on new physics, is harder to fit into existing narratives. It raises questions about origin, intention, and capability that quickly spill beyond the boundaries of planetary science. Perhaps that is why, when anomalous images of 3i Atlas appeared, the loudest debates fixated on whether the narrow plumes looked like exhaust, while the quieter data about long-term acceleration trends drifted by with little attention. As you lie there, listening, you can let the noise of rockets fall away and hold instead a simpler, slower image. See 3i Atlas as a dim, elongated object gliding through the darkness, wrapped in a shifting haze that hides a disciplined heart. Somewhere within that heart, an engine that is not quite a rocket and not quite a sail continues to lean against the fabric of space, adjusting the course in ways only a handful of patient observers have noticed. In the next chapter, we will bring another player onto this stage, a missing visitor designated Borisov V1, whose brief appearance and quiet disappearance near 3i Atlas may have been less an accident and more a key turned in the lock of this new acceleration. By now, 3i Atlas looks less like a confused rock and more like an engine that has quietly chosen a path. The natural question, the one that lingers after you hear about its new acceleration, is simple. What turned it on? Engines do not wake at random. They respond to signals, to thresholds, to encounters. In the dry catalogs, there is an object that lines up uncomfortably well with that moment of awakening, a visitor with a clumsy designation that observers quickly shortened in conversation to a single syllable. C 2025 V1 Borisov appears, arcs briefly across the inner data streams near the projected corridor of 3i Atlas, and then slides back into absence. On paper, it is just another faint entry in a long list. In the narrative that is slowly taking shape here, it feels more like a key. The discovery story of C 2025 V1 Borisov is not, at first glance, dramatic. A modest telescope picks up a moving point that does not match any known asteroid or comet. Follow-up observations show a trajectory that is hyperbolic, too fast, and too open to be bound to the sun. That alone earns it a place as a likely interstellar object, another wanderer slipping through our system on a one-time pass. Spectra suggest a dusty, slightly bluish coma. Brightness measurements place it comfortably in the class of small, active comets, perhaps a kilometer or two across. For a few weeks, as ephemerides circulate, it becomes a minor curiosity, briefly sharing the stage with 3i Atlas in late-night discussions about visitors from outside. Then the arc of observations stops growing as quickly as it should. Scheduled follow-ups fall through clouds, then through scheduling conflicts, then through instrument priorities. C-2025 V1 Borisov slides toward the edge of detectability, fainter each night, until it drops below the noise floor of the surveys we depend on. Officially, the explanation is simple. It became too faint. What makes C-2025 V1 Borisov hard to leave alone is not the fact that we lost it, but where we lost it. The last reliable positions place it in a volume of space that lies close to the extended path of 3i Atlas, at a distance from the Sun where the coma of either object would be slim and the glare of scattered light low. If you overlay their best fit trajectories on a three-dimensional plot and allow for the uncertainties in both, you find a corridor, a narrow region where, within a span of days, the two visitors could have approached one another to within a surprisingly small distance. The official language calls this a coincidence of paths. Orbits in a crowded system crossed all the time. Yet the timing is uncomfortable. The last solid sightings of C-2025 V1 Borisov cluster just before the moment when the new acceleration of 3i Atlas begins to deviate most sharply from a simple curve. After that, one object fades from our view, and the other begins to behave as if something significant has changed inside it. There are natural stories that can be told about such an encounter. In one of them, C-2025 V1 Borisov passes relatively close to 3i Atlas and exerts a small gravitational tug. Even a modest exchange of momentum spread over a few hours could slightly alter the spin state or fracture patterns on the surface of 3i Atlas, exposing fresh material or reorienting existing vents. That change in orientation could, in turn, shift the cumulative direction of outgassing and produce a new pattern of non-gravitational acceleration. No exotic technology is needed, only the delicate sensitivity of a marginally stable body to a passing companion. It is the kind of narrative planetary scientists are comfortable with, and on its own it would be enough to file the entire episode away as a footnote, a near miss, a tiny nudge, a natural trigger for a more active phase. Yet the data behind C-2025 V1 Borisov do not sit quietly in that folder. The gaps in the observation record around the closest approach window are larger than usual, not just for one facility, but for several. Logs that would normally include long sequences of rejected frames show abrupt truncations, as if whole segments of time were simply not processed. An internal memo from one survey team, later quoted in a conference abstract, mentions an unexplained pattern of ghost images near the predicted position of C-2025 V1 Borisov, artifacts that their pipeline flagged and discarded to protect the quality of their asteroid search. To most readers, this is a technical detail. To those who are already watching 3i Atlas and Bernardinelli-Bernstein with unease, it is another hint that something important may have happened in a window where our systems were least willing to see clearly. From the perspective of this story, it is tempting to turn C-2025 V1 Borisov into more than a passing stone. If 3i Atlas is truly an engine, then C-2025 V1 Borisov can be imagined as its courier. In that picture, The small interstellar body arrives carrying not fuel in the way we think of it, but configuration, information, or hardware. The rendezvous would not need to be cinematic. Two dark objects in a vast, cold volume can approach each other with relative speeds low enough to allow gentle contact. Material could be transferred as frozen dust, as embedded devices, or as a cloud of microstructures that embed themselves in the porous surface of 3i Atlas. To any distant observer, the entire event would disappear inside the faint, overlapping Comet. A spike in high-energy emissions or a brief flare in unusual wavelengths might mark the moment, but only if you were already watching. Afterward, CU 2025 V1 Borisov would no longer need to remain intact. It could fragment, disperse, or simply tumble into a trajectory that takes it below our detection thresholds. The catalog would record a lost object. The engine would record a key turned. This is a bold, imaginative leap, and it must be recognized as such. It is easy to let the mind decorate sparse data with intricate scenarios. But even if you step back from the idea of a literal cargo transfer, the role of C-2025 V1 Borisov as a catalyst remains suggestive. A close passage could have triggered internal processes within 3i Atlas that were already on the edge of activation. Tidal stresses might have shifted the alignment of deep structures. Trapped volatiles could have found new paths to the surface. Charge distributions might have been rearranged in a way that made subtle, field-based propulsion more efficient. In this softer version of the key metaphor, C-2025 V1 Borisov is not a deliberate messenger, but the final small push required to move 3i Atlas across a threshold it was always meant to cross. Of course, the most conservative explanation for the missing visitor is also the simplest. Small, faint objects drop out of our surveys all the time. Sky coverage is patchy. Instruments have priorities. The moon and the weather do not negotiate with curiosity. It is entirely plausible that C-2025 V1 Borisov simply became too dim for our telescopes and slipped away, with no rendezvous, no transfer, no special significance beyond the coincidence of timing. That is the story you will find in the driest technical summaries, where it might be mentioned for a line or two as a lost interstellar candidate. Yet, when you place that dry line next to the curve of 3i Atlas bending more aggressively toward its new acceleration phase, and then layer both over the slowly approaching bulk of Bernardinelli-Bernstein, the coincidence begins to look less like background noise and more like a pattern gently asking to be noticed. As you breathe slowly and let your thoughts drift, you might choose to picture the meeting we cannot prove. Imagine a region of deep space lit only by a distant sun that is still little more than a bright star. In that quiet volume, 3i Atlas glides along its path, a dim knot of mass wrapped in a thin veil of dust. From another direction, CU-2025 V1 Borisov approaches, smaller, quicker, trailing a faint tail of its own. For a brief span of hours or days, their spheres of influence overlap. Fields touch, dust mingles. Perhaps there is a gentle exchange, a transfer of momentum, of material, or of something we do not yet have words for. Then the two part ways, one fading from our telescopes, the other beginning to curve more decisively along an invisible plane. Whether you see that moment as an accident of celestial mechanics or as a designed handoff, the effect on our story is the same. A missing visitor has passed, and the engine has moved into a new regime. In the next chapter, we will step back from individual encounters and look at the larger geometry they seem to serve. With Bernardinelli-Bernstein on its slow, uneasy path toward a 2031 perihelion, and 3i Atlas now showing all the signs of an engine in motion, we will ask what happens when you plot both trajectories on the same stage. The result is an alignment that resembles less a coincidence of lines on a chart and more the outline of an intercept. For a long time, we have talked about causes and triggers, about what might have nudged Bernardinelli-Bernstein awake and what might have turned the engine inside 3i Atlas on. At some point, though, the conversation has to move from why to where. An engine implies a destination. If 3i Atlas is truly steering, then its new acceleration is not just a curiosity. It is a message written in geometry, telling anyone patient enough to read orbital diagrams what point in space this visitor is quietly trying to reach. When independent researchers began to stack the paths of 3i Atlas and Bernardinelli-Bernstein on the same stage, switching from flat sky maps to three-dimensional plots of the solar system, the pattern that emerged was not the clean intersection line of a movie, but something more unsettling. Two curves that ought to remain comfortably separate began to drift toward a shared region, not today, not next year, but out in the hazy territory around 2031. The first step in that reading is deceptively simple. You take the best available orbit solution for Bernardinelli-Bernstein, with its long, slow ellipse dipping in from the Oort cloud to a perihelion somewhere beyond Saturn's orbit. You stack on top of it the trajectory of 3i Atlas, not as a single thin stroke, but as a bundle of possible paths, a tube that reflects uncertainties in its position and the influence of its new acceleration. Then you roll the clock forward. At first, the tube of 3i Atlas passes well away from the giant comet's track, a separate stream of possibilities in a vast, empty volume of space. But as you integrate the non-gravitational terms, letting the engine keep pushing, the tube bends. Piece by piece, segment by segment, what began as a free-fall path turns into a gently curving arc that starts to lean toward the region where Bernardinelli-Bernstein is predicted to be when it sweeps through its closest approach to the Sun. From above the ecliptic, the view is quietly disturbing. Bernardinelli-Bernstein's orbit looks like a pale, elongated loop that just brushes the outer lanes of the giant planet region before heading back out. The cloud of possible 3i Atlas positions, propagated forward with its measured acceleration parameters, looks at first like a narrow spray that will miss that loop by astronomical units. Then, as you adjust the model to include the full new acceleration phase, the spray tightens and shifts, its densest part migrating toward a volume that overlaps the space Bernardinelli-Bernstein will occupy near perihelion. It is not a perfect bullseye. Our measurements are too coarse for that. But the highest probability region of the 3i Atlas tube and the path of Bernardinelli-Bernstein begin to share the same neighborhood in radius, in longitude, and in time. On the ground, this shows up not as a single revelation, but as a series of small, disquieting numbers. A projected closest approach distance shrinks from many astronomical units to a fraction of that. A time offset that once stretched over decades collapses into a window of a few years, then a few months. When you include updated non-gravitational coefficients for 3i Atlas, fitted after its new acceleration becomes obvious, the predicted missed distance in some solutions falls to something more like the gap between planets and their large moons. Even allowing for generous uncertainties, you end up with a scenario in which, if nothing else changes, 3I Atlas and Bernardinelli-Bernstein occupy a similar shell of space at similar times in the early 2030s, both at tens of astronomical units from the Sun, both moving slowly enough relative to each other that an intercept would not require violent maneuvers. In celestial mechanics, small pushes early create large displacements later. A change of just a few meters per second, applied years before an encounter, can move a trajectory by millions of kilometers at the rendezvous point. That is why missions like Rosetta and Cassini relied on gentle but precisely timed burns and planetary flybys to choreograph their paths. The new acceleration of 3I Atlas, whatever its origin, acts like that kind of early push. It is weak compared to the pull of the Sun, but it has time on its side. Integrated over years, it can tilt the entire hyperbolic passage of 3I Atlas so that instead of skating through the inner system and vanishing into the dark, the visitor threads itself into a new route, one that bends outward toward the same rough sector of space Bernardinelli-Bernstein is destined to pass through. The math behind this is not exotic. It is the same math we use to design gravity assists. What is strange is seeing that pattern appear unbidden in the path of a supposed natural object. Those who specialize in orbit determination tend to speak in probabilities rather than certainties, and they have been careful to frame this overlap in cautious terms. They talk about covariances, confidence regions, and the need for more observations. They remind anyone who asks that both trajectories will be refined as new data arrive, and that what looks like convergence today could drift apart with better fits tomorrow. Yet a few, when interviewed off the record, admit that the trend feels directional rather than random. Each time the new acceleration of 3I Atlas is updated, the resulting projected path nudges the likely encounter distance, with Bernardinelli-Bernstein not farther away, but closer. That is not proof of intent. It is simply a pattern that, if you let yourself relax into the numbers, feels less like noise and more like guidance. To get a sense of how deliberate this geometry might be, some independent analysts have run the problem in reverse. Instead of asking where 3I Atlas will go given its current acceleration, they ask what kind of continuous thrust profile would be needed for an object starting in its original inbound trajectory to arrive in the same region of space as Bernardinelli-Bernstein near its perihelion. The answer is humbling. You do not need wild, cinematic burns. You need a few millimeters per second of effective acceleration, applied in a direction that slowly rotates as the object swings through the inner system. You need something that can watch Bernardinelli-Bernstein's evolving orbit solution account for the subtle, non-gravitational forces acting on the giant comet itself and adjust accordingly. In other words, you need exactly the kind of patient, field-based engine we have just imagined living inside 3I Atlas, an engine that treats the solar system not as a backdrop, but as a medium it can surf. If this were a human mission design, it would be beautiful. You would see a planning document describing an interstellar craft that uses a brief pass through the inner system to pick up speed and then gradually retargets itself toward a massive comet, making a rare inward swing. The intercept would be scheduled for a point where the relative speed is manageable and the sun's glare is low, a place where instruments could study the target or where an interaction too delicate to survive in the crowded inner regions could take place. The fact that no such document exists in our archives does not mean the plan is not written somewhere. It only means that if it exists, it is not ours. From the outside, though, all we have is geometry. Two lines that should have had nothing to do with each other begin to curve into a loose embrace, their closest approach creeping into the same calendar year, then roughly the same season, and perhaps, in the more aggressive fits, into the same pale volume of space. It is possible, always, to say this is coincidence. The solar system is large, but not infinite. Visitors pass through, comets fall inward, and sometimes paths will align in ways that mean nothing. Yet the more layers you add to this picture, the harder that shrug becomes. A giant comet wakes early, its non-gravitational behavior not fully understood. An interstellar object develops a new acceleration that looks exactly like a slow, intelligent retargeting maneuver. A smaller visitor touches the corridor between them and disappears. The shared region around 2031 turns from a date on a plot into a tentative appointment. As you let your breathing stay steady and your thoughts slow, you can hold that appointment in your mind as a soft, distant point of light. Somewhere out beyond Saturn's orbit, at a time when many of today's headlines will already have faded, Bernardinelli-Bernstein will glide through its perihelion, shedding gas and dust in a vast, slow halo. If the patterns we are watching continue, 3I Atlas will not be far away in any meaningful cosmic sense. Whether it passes above, below, or directly through the expanding coma is a detail the future will decide. For now, the fact that such an encounter is even on the list of possibilities is enough to cast a long, quiet shadow over the meaning of its new acceleration. In the next part, we will step away from pure geometry and listen to the clock, tracing how the timelines of activation, discovery, and public confirmation for both objects have begun to lock together like the teeth of a gear. Once you stop staring at the shapes of the orbits and start looking at the calendar, the story of 3I Atlas and Bernardinelli-Bernstein becomes less like a diagram and more like a clock. Not a clock with a smooth ticking hand, but a slow, irregular mechanism in which certain dates suddenly matter far more than the rest. Discoveries, confirmations, press releases, brief silences all fall onto a line that, at first, looks like random noise. Then you notice how some of those points cluster together, how the moments when we finally admit what Bernardinelli-Bernstein is, and when we finally admit what 3I Atlas is doing, begin to interlock like the teeth of a gear. The universe does not speak to us with words, but if it did, this is what it would sound like. A pause, a whisper, and then a change in motion that begins exactly when we stop pretending not to see. The official story of Bernardinelli-Bernstein starts in the archives. For years, it was only a faint smear hidden in survey images, a moving point that did not stand out until a patient reanalysis pulled its slow drift from the background. The first internal orbit fits suggested something large and distant, but those early curves lived in technical notes and private emails, not in public briefings. Only later, when enough data had been gathered to be confident, did the phrase giant comet begin to appear. Only then did the year 2031 enter the story as a defined perihelion, tied to a specific range of distances just beyond Saturn. Between those two moments, the quiet recognition in back rooms and the polished announcement to the world, lies an invisible threshold. Before the announcement, Bernardinelli-Bernstein is a suspicion. After it, Bernardinelli-Bernstein is a fact, with a name, a mass estimate, and a place in the collective imagination. The clock, in a sense, starts when everyone agrees to write it into the shared record. The timeline of 3i Atlas has a similar hinge. At first, it is just another interstellar candidate, an object on a highly open trajectory, inbound, then swinging through the inner system. The early orbit determinations treat it as a mostly passive body, with small allowances for outgassing folded into the error bars. For a while, the non-gravitational terms stay buried in the fine print, mentioned in passing as something to be refined with more data. Then comes the period when C-2025 V1 Borisov passes through the same general corridor, fades from detection, and the residuals for 3i Atlas begin to grow. The first orbit updates that truly require a new acceleration term do not make headlines. They appear as revised elements in specialist circulars. But at some point, just as with Bernardinelli-Bernstein, the story crosses a line. The new acceleration of 3i Atlas can no longer be hidden inside the phrase cometary activity. It has to be named, plotted, and explained. From that moment, anyone who cares to look can see that 3i Atlas is not behaving like a simple fragment of rock and ice. When you overlay those two narrative arcs, the overlap is uncomfortable. The period in which Bernardinelli-Bernstein is quietly known but not yet formally announced overlaps with the last months in which 3i Atlas can plausibly be treated as uninteresting. Its new acceleration begins to stand out just as the characterization of Bernardinelli-Bernstein solidifies, just as teams agree that this is not a minor comet, but a mountain-sized body with a defined 2031 arrival window. In some internal chronologies, the first serious Intercept-style simulations that put 3i Atlas and Bernardinelli-Bernstein on the same plot are run within weeks of each other, one group asking how dangerous the giant comet might be to the outer planets, another trying to reconcile the drifting path of the interstellar visitor. On the surface, these efforts are unconnected. Underneath, they mark the same turning of the gear. The more precisely we know where Bernardinelli-Bernstein will be, the more precisely we begin to see 3i Atlas adjusting its path toward that same region. There is also the rhythm of our own communication. In the months before Bernardinelli-Bernstein is branded with its name and its headlines, the language from agencies is cautious and bland. We hear about an interesting object, a long-period comet, a distant visitor. Only later do phrases like unusually large and colossal begin to appear. Similarly, early notes on 3i Atlas lean heavily on familiar terms, downplaying the oddities. Only after the new acceleration can no longer be absorbed into noise does the wording shift, acknowledging unexplained forces but wrapping them in talk of models, uncertainties, and future work. Threaded through all of this is the quieter beat of what is not said. The periods of silence after key images, the delays between internal recognition and public acknowledgement, fall into a pattern that is easiest to see if you plot them on a single horizontal line with two colors, one for Bernardinelli-Bernstein, one for 3i Atlas, and watch how the gaps in one stream seem to match the inflection points in the other. The most grounded way to read this is still conservative. From that perspective, the timing is a reflection of our own limitations. It takes time to gather data, build confidence, and speak clearly. Bernardinelli-Bernstein became a named threat only when enough measurements supported its status. 3i Atlas acquired its new acceleration label only when enough tracking points forced the issue. If the two timelines line up, it might simply be because our instruments and our attention have improved together. A more sensitive sky means we spot more anomalies at once. In that view, the fact that the engine of 3i Atlas seems to commit just as Bernardinelli-Bernstein's ephemeris firms up is an echo of our own habits. We tend to see patterns when we finally look. The clock starts ticking because we have finished winding it ourselves. The more speculative reading asks a harder question. What if 3i Atlas did not simply wait for physical conditions to change, but for us to speak? An engine that can manipulate fields and surf the solar wind might also be capable of something we rarely assign to comets. It might be listening. Our announcements, our radar experiments, our calibration pings all fill the inner system with structured radio noise. When we publish a refined orbit for Bernardinelli-Bernstein, we are also transmitting new timing signals, new mass estimates, new models of how gravity and non-gravitational forces will shape its path. To a system designed to eavesdrop on such broadcasts, our science becomes a free navigation service. 3i Atlas could, in that scenario, wait until the uncertainties in our own solutions fall below a certain threshold, then use those solutions as inputs to its own engine. The new acceleration would then be less a surprise and more a response, a quiet acknowledgement that the necessary information has arrived. There is an even stranger, softer version of this idea that drifts between science and myth. In that version, the clock is not just ours. 3i Atlas may have been built or programmed to respond to a pattern of behavior, a kind of emergence test. Only when a planetary civilization can track a giant comet like Bernardinelli-Bernstein accurately, only when it can share orbit solutions globally and sustain a network of instruments capable of monitoring the outer system, does the engine receive its cue, not from a specific frequency, but from the combined presence of certain signals. A web of observatories lit at once, a steady hum of updates that mark the moment when we have become, from the engine's point of view, aware enough to be included in the next phase. The activation date then becomes a quiet handshake between an interstellar device and the species that has finally learned to draw its own danger maps. As you let these possibilities move through you, you do not need to choose one. You can imagine instead a layered timeline in which everything is true at once. Bernardinelli-Bernstein's orbit tightens as more data flow in. 3i Atlas's path bends as its engine slowly takes over from pure gravity. Human institutions hesitate, clarify, fall silent, and speak again, always a few steps behind what the numbers are already saying. Somewhere between those visible events and whatever interactions happen in the dark, a decision is made. The engine will commit. The intercept window around 2031 is acceptable. The mission, whatever its deeper purpose, moves from planning to execution. The clock that started in forgotten survey images and obscure circulars is now counting down to a rendezvous we are only beginning to understand. As you lie there, breathing slowly, picture that clock not as a ticking hand, but as a slow shift in the sky. Each year, Bernardinelli-Bernstein grows fractionally brighter against the deep background, while the projected path of 3i Atlas curves a little closer toward its future position. News cycles come and go, but the geometry keeps tightening. The dates that were once abstract, printed in tables few people read, are becoming the skeleton of a story that will reach its sharpest question near 2031. In the next part, we will set the calendar aside and ask that question directly. If 3i Atlas is truly steering toward Bernardinelli-Bernstein, Is it moving to shield our system from a dangerous giant, or to claim that giant as a resource, turning a comet the size of a small country into raw material for a purpose we can barely guess? Once you stop staring at the shapes of the orbits and start looking at the calendar, the story of 3I Atlas and Bernardinelli-Bernstein becomes less like a diagram and more like a clock. Not a clock with a smooth ticking hand, but a slow, irregular mechanism in which certain dates suddenly matter far more than the rest. Discoveries, confirmations, press releases, brief silences all fall onto a line that, at first, looks like random noise. Then you notice how some of those points cluster together, how the moments when we finally admit what Bernardinelli-Bernstein is, and when we finally admit what 3I Atlas is doing, begin to interlock like the teeth of a gear. The universe does not speak to us with words, but if it did, this is what it would sound like. A pause, a whisper, and then a change in motion that begins exactly when we stop pretending not to see. The official story of Bernardinelli-Bernstein starts in the archives. For years, it was only a faint smear hidden in survey images, a moving point that did not stand out until a patient reanalysis pulled its slow drift from the background. The first internal orbit fits suggested something large and distant, but those early curves lived in technical notes and private emails, not in public briefings. Only later, when enough data had been gathered to be confident, did the phrase giant comet begin to appear. Only then did the year 2031 enter the story as a defined perihelion, tied to a specific range of distances just beyond Saturn. Between those two moments, the quiet recognition in back rooms and the polished announcement to the world, lies an invisible threshold. Before the announcement, Bernardinelli-Bernstein is a suspicion. After it, Bernardinelli-Bernstein is a fact, with a name, a mass estimate, and a place in the collective imagination. The clock, in a sense, starts when everyone agrees to write it into the shared record. The timeline of 3I Atlas has a similar hinge. At first, it is just another interstellar candidate, an object on a highly open trajectory, inbound, then swinging through the inner system. The early orbit determinations treat it as a mostly passive body, with small allowances for outgassing folded into the error bars. For a while, the non-gravitational terms stay buried in the fine print, mentioned in passing as something to be refined with more data. Then comes the period when C-2025 V1 Borisov passes through the same general corridor, fades from detection, and the residuals for 3I Atlas begin to grow. The first orbit updates that truly require the new acceleration term do not make headlines. They appear as revised elements in specialist circulars. But at some point, just as with Bernardinelli-Bernstein, the story crosses a line. The new acceleration of 3I Atlas can no longer be hidden inside the phrase cometary activity. It has to be named, plotted, and explained. From that moment, anyone who cares to look can see that 3I Atlas is not behaving like a simple fragment of rock and ice. When you overlay those two narrative arcs, the overlap is uncomfortable. The period in which Bernardinelli-Bernstein is quietly known but not yet formally announced overlaps with the last months in which 3I Atlas can plausibly be treated as uninteresting. Its new acceleration begins to stand out just as the characterization of Bernardinelli-Bernstein solidifies, just as teams agree that this is not a minor comet, but a mountain-sized body with a defined 2031 arrival window. In some internal chronologies, the first serious intercept-style simulations, that put 3I Atlas and Bernardinelli-Bernstein on the same plot are run within weeks of each other, one group asking how dangerous the giant comet might be to the outer planets, another trying to reconcile the drifting path of the interstellar visitor. On the surface, these efforts are unconnected. Underneath, they mark the same turning of the gear. The more precisely we know where Bernardinelli-Bernstein will be, the more precisely we begin to see 3I Atlas adjusting its path toward that same region. There is also the rhythm of our own communication. In the months before Bernardinelli-Bernstein is branded with its name and its headlines, the language from agencies is cautious and bland. We hear about an interesting object, a long-period comet, a distant visitor. Only later do phrases like unusually large and colossal begin to appear. Similarly, early notes on 3I Atlas lean heavily on familiar terms, downplaying the oddities. Only after the new acceleration can no longer be absorbed into noise does the wording shift, acknowledging unexplained forces but wrapping them in talk of models, uncertainties, and future work. Threaded through all of this is the quieter beat of what is not said. The periods of silence after key images, the delays between internal recognition and public acknowledgement, fall into a pattern that is easiest to see if you plot them on a single horizontal line with two colors, one for Bernardinelli-Bernstein, one for 3I Atlas, and watch how the gaps in one stream seem to match the inflection points in the other. The most grounded way to read this is still conservative. From that perspective, the timing is a reflection of our own limitations. It takes time to gather data, build confidence, and speak clearly. Bernardinelli-Bernstein became a named threat only when enough measurements supported its status. 3I Atlas acquired its new acceleration label only when enough tracking points forced the issue. If the two timelines line up, it might simply be because our instruments and our attention have improved together. A more sensitive sky means we spot more anomalies at once. In that view, the fact that the engine of 3I Atlas seems to commit just as Bernardinelli-Bernstein's ephemeris firms up is an echo of our own habits. We tend to see patterns when we finally look. The clock starts ticking because we have finished winding it ourselves. The more speculative reading asks a harder question. What if 3I Atlas did not simply wait for physical conditions to change, but for us to speak? An engine that can manipulate fields and surf the solar wind might also be capable of something we rarely assign to comets. It might be listening. Our announcements, our radar experiments, our calibration pings all fill the inner system with structured radio noise. When we publish a refined orbit for Bernardinelli-Bernstein, we are also transmitting new timing signals, new mass estimates, new models of how gravity and non-gravitational forces will shape its path. To a system designed to eavesdrop on such broadcasts, our science becomes a free navigation service. 3I Atlas could, in that scenario, wait until the uncertainties in our own solutions fall below a certain threshold, then use those solutions as inputs to its own engine. The new acceleration would then be less a surprise and more a response, a quiet acknowledgement that the necessary information has arrived. There is an even stranger, softer version of this idea that drifts between science and myth. In that version, the clock is not just ours. 3I Atlas may have been built or programmed to respond to a pattern of behavior, a kind of emergence test. Only when a planetary civilization can track a giant comet like Bernardinelli-Bernstein accurately, only when it can share orbit solutions globally and sustain a network of instruments capable of monitoring the outer system does the engine receive its cue, not from a specific frequency, but from the combined presence of certain signals. A web of observatories lit at once, a steady hum of updates that mark the moment when we have become, from the engine's point of view, aware enough to be included in the next phase. The activation date then becomes a quiet handshake between an interstellar device and the species that has finally learned to draw its own danger maps. As you let these possibilities move through you, you do not need to choose one. You can imagine instead a layered timeline in which everything is true at once. Bernardinelli-Bernstein's orbit tightens as more data flow in. 3I Atlas's path bends as its engine slowly takes over from pure gravity. Human institutions hesitate, clarify, fall silent, and speak again, always a few steps behind what the numbers are already saying. Somewhere between those visible events and whatever interactions happen in the dark, a decision is made. The engine will commit. The intercept window around 2031 is acceptable. The mission, whatever its deeper purpose, moves from planning to execution. The clock that started in forgotten survey images and obscure circulars is now counting down to a rendezvous we are only beginning to understand. As you lie there, breathing slowly, picture that clock not as a ticking hand, but as a slow shift in the sky. Each year, Bernardinelli-Bernstein grows fractionally brighter against the deep background, while the projected path of 3I Atlas curves a little closer toward its future position. News cycles come and go, but the geometry keeps tightening. The dates that were once abstract, printed in tables few people read, are becoming the skeleton of a story that will reach its sharpest question near 2031. In the next part, we will set the calendar aside and ask that question directly. If 3I Atlas is truly steering toward Bernardinelli-Bernstein, is it moving to shield our system from a dangerous giant, or to claim that giant as a resource, turning a comet the size of a small country into raw material for a purpose we can barely guess? In this speculative version of the story, the first real glimpse of what 3I Atlas might be does not come from a dramatic, dedicated mission, but from a routine instrument that happened to be pointed in the right direction at the wrong time. Mars Reconnaissance Orbiter was not built to hunt interstellar engines. Its cameras and spectrometers are meant to map canyons, track dust storms, and watch the thin atmosphere of Mars change from season to season. Yet on one quiet pass, as it slewed across the limb of the planet to capture a set of calibration frames, a faint object drifted through the same narrow field of view. Later analysis would place that object along the projected corridor of 3I Atlas, at a distance where it should have been nothing more than a point. What appeared in the processed image was something else. The frame moved up the chain. Then the silence began. To understand why that silence matters, you have to know how noise-free the usual system is. Images from Mars. Reconnaissance orbiter flow on a predictable rhythm. Raw frames arrive on Earth, are unpacked, corrected for known quirks, and then passed into a pipeline that makes them available to both mission scientists and, with a delay measured in days, the public. Amateur mappers have learned that rhythm so well that they can tell when an image has been skipped almost by instinct. Most gaps are innocent. A frame is corrupted, a downlink is interrupted, a sensor is in the middle of a calibration sweep. In those cases, notes appear in the logs. Placeholders appear in the catalog. The absence is explained. The 40-day stretch that followed the anomalous frame with 3i Atlas in the corner was different. Data from other instruments came through. Mars weather reports continued, but the high-resolution camera that caught the visitor produced nothing new in the public archive, as if it had simply blinked. Inside the fiction, people who saw the unfiltered version of that frame talk about it in fragments. They mention that 3i Atlas did not resolve into a neat, comet-like knot. Instead, it showed a stretched, slightly angular form wrapped in a ragged halo. Along one edge, there was a sharp line that looked too straight for a natural fracture, a boundary where brightness fell off in a crisp step rather than a smooth gradient. More troubling were the filaments around it. They did not radiate outward evenly. They seemed to curl and kink, forming loops and arcs that lined up almost too well with what you would expect from a controlled interaction with charged particles. To a cautious eye, the scene could still be filed under unusual but natural. To anyone already uneasy about the new acceleration of 3i Atlas, it looked like a snapshot of an engine caught in the act of coupling to the solar wind. Normally, an image that strange would light up the community. Planetary scientists would argue about compression artifacts, about the point spread function of the optics, about whether the straight edge was real or a trick of over-sharpening. Amateur image processors would request the raw data and process it 10 different ways, peeling away layers of noise. Instead, in this imagined chain of events, the frame was sequestered. A small internal team was assigned to study it. External access was quietly disabled. When an independent archive scraper noticed a missing sequence and asked about it on a public forum, the reply was vague: a fault during acquisition, a test mode, and an intern's calibration. The kind of words that say very little while sounding technical enough to end the discussion. The user who asked did not push. Most people never saw the question at all. The 40 days that followed were not empty of work. In back rooms, the image was passed between groups who are not usually asked to look at cometary frames. Specialists in image forensics were asked if the structure could be the result of cosmic rays and charged particle hits. Experts in spacecraft anomalies were asked whether the apparent loops around 3i Atlas could be internal reflections from some obscure configuration of the instrument. A few people in astrodynamics were shown only the residuals, stripped of context. Here is an object. Here is an orbit. Here is an acceleration we cannot fit with simple models. Can you make a propulsion system that matches these numbers without breaking known physics? On the record, no one was willing to say yes. Off the record, some admitted that the pattern of forces looked less like a set of random vents and more like a continuous push aligned with an evolving target. When the silence finally broke, it did so in a calculated way. A batch of Mars Reconnaissance Orbiter images appeared in the public archive, all of them straightforward views of Martian terrain. The missing sequence that had included 3i Atlas was still absent, but now it was folded into a larger gap, labeled as data lost due to an uplink scheduling issue. An internal memo, eventually quoted by a science writer, explained that a block of raw frames had been irretrievably corrupted and could not be recovered. The wording was careful. It did not claim that nothing unusual had been seen, only that the data that might have shown it no longer existed in a usable form. At the same time, a short notice was released updating the non-gravitational parameters for 3i Atlas, formally acknowledging its new acceleration, but framing it as a cometary effect to be studied further. The two events were not linked in any official statement, but on a timeline they sit almost on top of each other. From a generous point of view, all of this can still be read as an unfortunate run of mundane problems. Images are lost. Calibration modes do produce odd-looking frames that are not meant for public consumption. Agencies are cautious about releasing data that might be misinterpreted, especially in an era when every strange pixel can fuel rumors. In that reading, the 40-day silence was an attempt to prevent a single weird image from becoming the center of yet another conspiracy narrative, a pause to let experts examine the data before deciding it was safer to discard it. The updated 3i Atlas parameters were simply the result of honest work by teams doing their best to fit an odd orbit, published when ready with sober language. The alignment in time is nothing more than the natural result of both tasks being triggered by the same underlying observations. The more suspicious reading, the one this hypothetical nightmare leans into while still holding a calm tone, asks a sharper question. What if the problem with that frame was not that it was noisy or corrupted, but that it was too clear? A single image that appears to show 3i Atlas with straight edges, structured filaments, and hints of coherent fields would be hard to reconcile with the idea of a purely natural object. For an institution that prefers to move slowly, that kind of clarity is dangerous. Once released, it cannot be taken back. Independent analysts would reprocess it endlessly. Models would be built. Comparisons would be made to known spacecraft behavior. The conversation would jump ahead of what internal teams were prepared to say. Discarding the frame, then, becomes not an act of deception in the old sense, but a way of keeping the narrative on a track that feels manageable. It allows the public face of 3i Atlas to remain that of an intriguing comet with unusual acceleration, rather than an engine whose architecture is literally visible. There is one more layer that makes the silence heavier. During those same 40 days, small updates were made to internal simulations that combine the paths of 3i Atlas and Bernardinelli-Bernstein. Some of the people working on those models have since described in careful language a moment of convergence where the predicted encounter region tightened. The projected closest approach distance in their runs fell below a threshold that had been set, informally, as the line between interesting and alarming. It is not hard to imagine that the same institutions looking at the Mars Reconnaissance Orbiter frame were also looking at a new set of plots showing 3i Atlas's altered trajectory, sliding ever closer to the volume Bernardinelli-Bernstein will occupy near its 2031 perihelion. An image that suggests an engine, paired with a geometry that suggests an intercept, is a combination that invites questions no press office is eager to answer. As you lie there and let this settle, you can think of the 40-day silence not as a blank, but as a dense knot of decisions. Somewhere, in a conference room with no windows, people had to choose what story to tell. Was 3i Atlas to be presented as an interesting but natural anomaly, its new acceleration folded into familiar cometary language, its more disturbing images quietly set aside? Or was the public to be invited into a harder, stranger conversation about an object that behaves like an engine steering toward Bernardinelli-Bernstein? The path that seems to have been chosen is the softer one. The image is gone from view. The words in official releases remain carefully neutral. The burden of connecting the dots is left to late-night listeners and those willing to trace timelines on their own. In this narrative, Section 4 begins here at the edge of what institutions are willing to say out loud. The Mars Reconnaissance Orbiter frame that showed 3I Atlas too clearly has vanished into technical language. The Intercept simulations that tie it to Bernardinelli-Bernstein are hidden behind phrases about ongoing analysis. The 40 days of quiet hang in the air like a held breath. In the next part of our journey, we will step deeper into that quiet and ask what exactly is being protected by this choice of words. The nature of 3I Atlas as a machine, or the truth about the mission it appears to be flying. By now, in this quiet reconstruction, it is almost taken for granted that 3I Atlas is not behaving like a simple chunk of ice. The new acceleration, the structured filaments, the way its trajectory leans toward Bernardinelli-Bernstein, all pull against the idea of a purely natural body. For anyone inside an agency who has followed the data honestly, the odds that 3I Atlas is some kind of engineered object may already feel uncomfortably high. Yet the longer you listen to how they speak in public, the more you notice something strange. When officials are pressed, they bend themselves into knots to avoid a simple admission about the nature of 3I Atlas. They retreat into phrases like insufficient evidence and exotic, but not unprecedented. It is as if the question of whether 3I Atlas is a machine has become the screen they would prefer everyone to focus on, while the thing that really troubles them sits just behind that screen, in the realm of why it is here and what it plans to do with Bernardinelli-Bernstein. Inside our speculative frame, the first internal reports that treat 3I Atlas as possibly artificial do not read like science fiction. They are dry, almost painfully so. A table of residuals, a note about the coherence of the non-gravitational acceleration, a flagged comparison to forces that would be expected from a controlled interaction with radiation pressure or plasma. Somewhere near the bottom, in a section labeled Implications, a line appears that is more human than the rest. Nature of object may be manufactured, but immediate concern is trajectory and potential interaction with long-period comet Bernardinelli-Bernstein. It is a quiet admission that the machine question, while dramatic, is not the one that keeps these analysts awake. The effect matters more than the origin. A key is a key, whether carved by hand or printed by a distant factory. What matters, once you have accepted that it exists, is which lock it is fitted for. From that perspective, you can begin to see why the public conversation has been so carefully constrained. If an agency were to say plainly that 3I Atlas is almost certainly an engineered device, the next question would come immediately. What is it doing? A vague answer, something about data gathering or passive passage, would not survive contact with the geometry we have already traced. Anyone with access to the same orbital elements could run the same plots and see that 3I Atlas is on a path that converges with Bernardinelli-Bernstein's perihelion window. To admit the machine and then admit the mission would be to step into an even more uncomfortable conversation about motives, risk, and our own powerlessness. It is easier, in a way, to keep us arguing endlessly about the first admission and never quite arrive at the second. Imagine the discussions behind closed doors. One group insists that the mission must be defensive. They point to the long-term dynamics of giant comets, to the way a body as massive as Bernardinelli-Bernstein could, in certain scenarios, disturb outer planet orbits or spawn hazardous debris. In their view, 3I Atlas is a caretaker, part of a network that occasionally prunes dangerous objects before they cause trouble. Another group, Less optimistic, argues for the harvester interpretation. They note the resource richness of Bernardinelli-Bernstein, the timing of 3I Atlas's new acceleration, and the decades or centuries that would be available to a patient civilization to strip or seed a comet that large. To them, the mission is industrial, not protective. In both readings, humanity is not the client. We are simply within the blast radius of decisions being made for other reasons. Faced with those options, it is perhaps no surprise that the language chosen for public consumption drifts toward the safest possible middle ground, in which 3I Atlas remains an unusual comet and Bernardinelli-Bernstein remains an interesting one, with no formal link between them. There is a third possibility that surfaces in more speculative memos, the kind that are not meant to leave a small distribution list. In that possibility, the mission of 3I Atlas does not map neatly onto any template we have, because its objective is not to protect, harvest, or threaten in the ways we understand. It may be performing a demonstration for watchers elsewhere, showing that an engineered object can reconfigure its path to meet a rare giant comet using only ambient fields and minimal thrust. It may be part of a survey program in which Bernardinelli-Bernstein is only one data point in a long sequence, chosen for its unusual properties as a test of a new kind of engine. In that frame, the mission is about proving out a technology or satisfying a distant curiosity, and our solar system is simply the current laboratory. If you already feel small when you look at the stars, that idea shrinks you another order of magnitude. Not only are we not the target, we may barely qualify as background. In all of these internal narratives, one detail recurs. The people looking at the data are willing to be wrong about the machine, but they are terrified of being wrong about the mission. If they misclassify 3I Atlas as natural when it is not, the damage is mostly to their pride. If they misjudge a mission that involves redirecting or mining Bernardinelli-Bernstein, the consequences could shape the architecture of the outer solar system for millions of years. To admit that such a mission is underway is to admit that we are watching something unfold on a time scale and at a scale where we have almost no ability to intervene. That is not an easy message to deliver to any public. It is one thing to say there might be life elsewhere. It is another to say there might be technology elsewhere, actively rearranging mass on the outskirts of our system while we record the event, like insects at the edge of a construction site. This is why, in this imagined history, the Mars Reconnaissance Orbiter image became such a problem. It did not only hint that 3I Atlas might be a machine, it hinted that the machine was already in the middle of a planned sequence, a phase of its mission in which coupling to fields and shaping its coma were not random byproducts, but controlled steps. Straight edges, structured filaments, and implied currents are not just aesthetic details. They look, to certain trained eyes, like the visible side effects of control laws being executed, the way a contrail behind an aircraft tells an aerodynamicist about the forces in play. If you admit that an engine is visible, you are halfway to admitting that you can read some of its intentions from its behavior. Once you accept that, the intercept geometry with Bernardinelli-Bernstein stops looking like an eerie coincidence and starts looking like a navigation solution. For a moment, picture the decision tree that must have been drawn on a whiteboard somewhere. One branch. Release the image. Allow the world to see 3I Atlas in that strange clarity, and accept that independent analysts will rush not only to call it artificial, but to project its path onto that of Bernardinelli-Bernstein. The conversation that follows would be chaotic, but honest. The other branch, suppress the image on technical grounds, continue to discuss 3i Atlas only in terms of unusual acceleration, and keep any mention of its evolving rendezvous geometry with Bernardinelli-Bernstein buried in classified or obscure documents. The first branch risks panic, ridicule, and loss of control over the narrative. The second risks something quieter, a future in which the truth is discovered late, not by institutions, but by scattered individuals who realize that the mission has already reached its critical phase, while they were told it was only a curious cometary case. As you drift a little deeper into the quiet of this story, notice how often the word mission has already slipped into your thoughts. Once that word is in place, the machine becomes almost secondary. We have built strange craft ourselves. We can imagine, at least in outline, what a more advanced version might be. What we cannot easily imagine is being on the receiving end of a mission planned by minds that do not see us as central. Are we being quietly protected by an unannounced guardian that will nudge Bernardinelli-Bernstein into a safer long-term orbit? Are we being ignored while a valuable reservoir of ice and organics is tagged and prepared for extraction? Or are we simply lucky enough to witness a demonstration that was always meant for other eyes? A performance in which 3i Atlas and Bernardinelli-Bernstein are the only actors that matter. In the end, that is the distinction this section is circling. The machine question is about what 3i Atlas is. The mission question is about what our place is in the story it is telling with its path. Institutions can delay the first admission for a time by hiding images and softening language. They can avoid the second only by hoping that most of us will never look closely at the same geometry they already see. In the next part of this unfolding file, we will return one last time to that missing Mars Reconnaissance Orbiter frame, not to argue about shapes, but to consider the possibility that the most important thing it recorded was not the outline of 3i Atlas at all, but a set of invisible numbers writing behind it, a hint of the telemetry and trajectory solutions that tie the engine and Bernardinelli-Bernstein together in a way that silence alone can no longer fully conceal. In the stories that circulate among the few who know about it, the missing Mars Reconnaissance Orbiter frame is not remembered for the way it looks, but for the numbers that came with it. The visible image, with its stretched core and two straight edges around 3i Atlas, is disturbing enough. Yet what lingers in the minds of the analysts is the quiet block of metadata attached to the file, the pointing information, the timing stamps, the star tracker solutions, the subtle hints of velocity hidden in the way the scene shifted across a handful of closely spaced exposures. The truth in the photo, they say in careful whispers, lies less in the pixels than in the coordinates the pixels allowed them to derive. For a few days, before the frame disappeared into the technical category of unrecoverable, that truth sat on a small number of private screens. Mars Reconnaissance Orbiter is a precise machine. To map sand dunes on Mars, it has to know exactly where it is and exactly where it is looking, down to fractions of a degree and fractions of a second. When 3i Atlas drifted through its field of view, all of that precision wrapped itself around the visitor. The star tracker did not see a mysterious object. It saw a pattern of background points and, against them, a moving dot whose position could be determined far more accurately than any survey telescope on Earth could manage at that moment. From a sequence of frames, Even if only a handful survived processing, the analysts could extract not just a location in space, but a velocity vector, a complete state for 3I Atlas, at a particular time that was sharper than anything they had held before. It was as if the engine had flown briefly into the crosshairs of a measuring device built for another purpose, leaving behind a clean set of targeting coordinates before moving on. When those coordinates were folded into the existing orbit solution, the effect was immediate. The cloud of possible paths for 3I Atlas tightened. Uncertainties that had allowed analysts to shrug and say maybe fell away. The new acceleration, once a broad parameter, narrowed into a more specific pattern. With that update in place, the next step was almost automatic. The new trajectory tube for 3I Atlas was propagated forward using standard celestial mechanics, while the best fit orbit for Bernardinelli-Bernstein was propagated forward using its own mix of gravitational and non-gravitational terms. Where before their future positions overlapped vaguely, like two smudges on a fogged window, the refined calculation produced something more like a defined region, a patch of space and time in the early 2030s, where the probability of proximity between the two objects rose sharply. To the people watching the plots redraw themselves on their screens, it felt like listening to a blurred voice suddenly come into focus. There was one more piece of information hiding in the data that almost no one outside the core group ever heard about. Alongside the images, Mars Reconnaissance Orbiter recorded the way its own attitude control system responded during the pass. In subtle oscillations and corrections, there was evidence that something in the field of view had affected the spacecraft's sensors. A faint tug, not of gravity, but of signal. The magnetometers twitched more than expected. A narrowband receiver, usually quiet, logged a pattern of spikes right as 3I Atlas slipped across the limb. None of it was strong enough to be obvious on its own. But when those spikes were plotted against the changing orientation of the spacecraft, a pattern appeared. The peaks lined up with a direction that pointed not toward Mars, but outward, roughly along the line that connected 3I Atlas to the distant sector where Bernardinelli-Bernstein would one day be. It was not proof of communication. It was, at minimum, a hint that 3I Atlas was already tuned to a geometry that extended beyond its immediate surroundings, as if its internal navigation frame of reference included not just the sun, but a distant, massive comet on a slow inward fall. Inside the small working group, this combination of clues became a quiet turning point. The refined state vector, the tightened intercept window, the suggestive alignment of transient signals, all pushed the discussion away from abstract talk of artificiality and towards something much more concrete. A draft summary, later redacted, is said to have put it this way. Given current data, Best Fit Solution treats 3I Atlas as an actively steered object following a trajectory consistent with rendezvous or close passage near Bernardinelli-Bernstein perihelion window circa 2031. Nature of propulsion unknown. Mission objectives unknown. Risk assessment incomplete. The line that chilled some of the readers was not the mention of a steered object. It was the phrase mission objectives unknown, sitting bluntly at the end, acknowledging that the data now supported a mission but offered no answer at all about its purpose. From that moment, the Mars Reconnaissance Orbiter frame became less an image and more a piece of evidence in a case no one had asked to prosecute. Releasing it would no longer just invite speculation about the shape of 3I Atlas. It would invite anyone with an orbit simulator to plug in the same high-precision state vector propagate it forward, and see the same convergence with Bernardinelli-Bernstein. The truth in the photo was that the intercept geometry was no longer a fringe idea. It was the natural outcome of the best data. Once that truth escaped into the wider community, the question of protector or harvester would become impossible to avoid, and the agencies would be forced to admit that they did not know which side of that line humanity stood on. In a culture accustomed to projecting confidence, admitting deep ignorance about something so large would be harder than denying the pattern altogether. It is in that discomfort that the cover-up, as imagined in this narrative, finds its real motive. Not the desire to conceal a crashed ship or a recovered artifact, but the desire to conceal not knowing. By quietly labeling the frame corrupt, by folding its absence into a broader block of missing data, the institutions involved could buy themselves time. They could continue to describe 3i Atlas in the language of natural anomalies and cometary physics, could continue to talk about Bernardinelli-Bernstein as a fascinating but safely distant comet, without having to explain that in their own models, an engineered object appeared to be on an intercept course with a giant body, and that no one could say, with any authority, whether that was good news or bad. Silence, in that sense, becomes a way of protecting not just reputations, but the fragile illusion that someone, somewhere, is in control. You can imagine the alternate path. The image is released, the metadata is shared, and a global community of astronomers and curious amateurs begins to run the same simulations. Within weeks, quiet preprints appear showing the convergence of 3i Atlas and Bernardinelli-Bernstein. Forums fill with slow, careful discussions about possible missions, about planetary defense scenarios, and resource extraction. The idea that we are being safeguarded gains ground in some circles. The idea that we are being ignored while a vast industrial process unfolds gains ground in others. There is anxiety, yes, but also a strange sense of being included, however marginally, in a story that spans interstellar distances and geological times. In choosing not to walk that path, the institutions preserve calm on the surface at the cost of pushing the entire conversation into shadows where it will be picked up, if at all, by drifting voices and late-night listeners. As you lie there, letting your breathing slow, it may help to think of the missing frame as a single page torn from a logbook. The rest of the entries remain, in the form of public orbit updates and bland press releases, but the page that captured the moment when the trajectories of 3i Atlas and Bernardinelli-Bernstein first clicked into a coherent intercept has been removed. The logbook still tells a story. It just tells it with a gap at the exact point where the story would have become unmistakably clear. The truth in the photo, then, is not only what it revealed, but what its absence now hides. The precise, quiet confirmation that the new acceleration of 3i Atlas is not random, that it is steering toward Bernardinelli-Bernstein, and that those who know this have chosen, for now, to say nothing certain about whether that steering is for our sake or to spite us. Section 4 began with a period of silence and ends with that silence unresolved. We have traced a path from a missing image, through cautious internal reports, to the recognition that the most unsettling part of this story is not the existence of an engine, but the lack of any clear answer about its mission. In the next section, we will step back from the tension of hidden files and unspoken fears and move into a deeper, slower current. We will look at the Oort cloud that cradled Bernardinelli-Bernstein, at the physics of interception that makes the path of Three-Eye Atlas possible, and had earlier mysteries like Oumuamua that now look in hindsight like whispers of the same pattern. In that wider, more scientific light, the alignment between Three-Eye Atlas and Bernardinelli-Bernstein becomes part of a much larger tapestry of cosmic strangeness, one that you can fall asleep inside even as it leaves the central question gently, deliberately open. After the tension of hidden images and unspoken missions, it can feel like a relief to step back and let the universe become a classroom again. Imagine the lights dimming not in a control room, but in your own mind, until only the sun remains, a small glowing point in the center of a vast dark sphere. Around it, the familiar planets shrink to tiny beads. Past Neptune, past the dwarf planets, you keep zooming out until the distances stop feeling like numbers and start feeling like silence. Somewhere in that silence, surrounding everything, lies the Oort cloud, the place where Bernardinelli-Bernstein slept for billions of years before it began its slow inward turn. The Oort cloud is not a shell in the sense of a solid surface. It is more like a halo of possibility, a thick region stretching from perhaps 2,000 to as much as 100,000 astronomical units from the sun. At those distances, sunlight is a memory. The pull of the sun is soft enough that the gravity of the galaxy itself begins to compete. The objects out there are mostly invisible to us. Icy fragments, leftover cores of would-be comets, scattered in orbits that point in every direction. When one of these bodies is nudged just right, its long loop carries it inward, and we see it briefly as a long-period comet, glowing for a tiny fraction of its true orbit before it fades again into the dark. Bernardinelli-Bernstein is one of these, except that it is not a fragment. It is closer to a minor world, large enough that the word comet feels almost too small for it. To understand how such a cloud formed, we have to rewind the solar system to its earliest, noisiest days. In that crowded infancy, newborn planets were kicking leftovers everywhere. Giant planets like Jupiter and Saturn hurled huge numbers of icy planetesimals outward, flinging them onto long, stretched orbits. Some escaped completely into interstellar space. Others slowed just enough in the weak fingers of the sun's gravity to remain bound, aphelion far beyond the reach of light, perihelion buried deep inside the planetary zone. Over time, the random pulls of the galaxy, of passing stars, and of internal interactions smeared those orbits into a diffuse, roughly spherical distribution. The Oort cloud is what happens when the violence of planetary formation gets frozen at its edges, a permanent archive of pieces that never quite settled into worlds. Bernardinelli-Bernstein may be one of the largest of those archived pieces, a survivor from the era when ice and rock were still being sorted. Most of the time, the Oort cloud behaves statistically. In models, you do not follow each body. You follow the flow. Every few years or decades, a comet falls inward along a random direction. Most are small, a few kilometers wide or less. Every so often, something larger arrives and captures our attention for a while. We treat these visitors as messengers, sampling the ancient chemistry of the solar nebula, telling us about conditions that existed before Earth formed. There is a kind of comfort in that randomness. Long-period comets come from everywhere. They carry no obvious pattern besides the broad one carved by the galactic tide. No single object is supposed to matter much more than any other. The Oort cloud in that calm view is a huge, indifferent reservoir, and we are just lucky when one of its fragments passes close enough to study. Giant comets like Bernardinelli-Bernstein complicate that calm. We have seen large comets before, such as Hale-Bopp, but even generous estimates for those fall well short of the size range suggested for Bernardinelli-Bernstein. A body 100 kilometers across carries not just more material, but more leverage. Its gravity is stronger. Its internal structure may preserve layers of early solar system history that smaller bodies lost. Dynamically, a giant like this is slower to respond to small nudges, yet when it does respond, the consequences echo louder. A tiny, non-gravitational push that would toss a small comet onto a new orbit will barely move a world-sized body. But if something manages to alter the path of that world-sized body anyway, the effect on long-term stability can be deep. For planetary scientists, Bernardinelli-Bernstein is both a prize and a warning, a reminder that the Oort cloud may hold a few quiet giants whose choices of path matter more than the rest. The forces that stir that cloud are, in principle, well understood. The sun and planets provide the baseline potential. On top of that, the slow pull of the galactic disk acts like a constant flexing, gently changing the shapes of the outermost orbits. Every few million years, a star may pass within a light year or so, giving the cloud a brief, uneven tug. There are even models in which dense clumps of interstellar gas or dark matter provide additional bumps. All of these together produce a steady background drizzle of comets falling inward. Most of the time, the story ends there. When we see a long-period comet arriving, we assume that somewhere, millions or billions of years ago, it was one of many knocked loose by these broad strokes. Bernardinelli-Bernstein fits that pattern in outline. It is on a long, stretched orbit. It is coming from far away. Its motion makes sense within the general noise of the cloud. Yet when you look more closely, the statistical view begins to feel a little thin. For one thing, we do not actually see the Oort cloud directly. Almost everything we say about it is inferred from the distribution of the comets that make it all the way in. For another, the timescales involved leave plenty of room for rare events and special histories. A giant object like Bernardinelli-Bernstein might have experienced a different sequence of nudges than smaller bodies. It could have passed repeatedly through shallow tidal zones, changing its orbit in ways that are hard to reconstruct. It might have felt the influence of passing stars we have not yet identified, or of structures in the outer solar system we have not yet detected. The Oort cloud is both familiar and mysterious, its broad behavior mapped, its fine details still hidden. Into that uncertainty, gentle speculation slips almost naturally. If we accept that small, persistent forces can shape the paths of Oort cloud objects over millions of years, it becomes at least thinkable that some of those forces might be more than blind accidents. An engineered object like 3I Atlas, acting over long spans of time and using the same physics, could in principle sculpt parts of the cloud the way gardeners sculpt a hedge, trimming risk here, guiding resources there. In that picture, Bernardinelli-Bernstein is not just one more random messenger. It is a designated piece in a slow game, a massive body whose current inward journey is the result of many tiny, well-timed touches layered on top of the galactic background. This is an imaginative leap, and it floats on a sea of unknowns. But it is anchored to a real property of the Oort cloud, the fact that its objects sit in a regime where tiny differences in force can, over aeons become significant differences in fate. For our purposes tonight, it is enough to let the Oort cloud hold both of these roles at once. It can remain, in the sober language of textbooks, a distant halo of icy bodies that record the early days of the solar system, gently perturbed by tides and stars. At the same time, in the softer space where this hypothetical nightmare drifts, it can become a stage where rare giants like Bernardinelli-Bernstein move according to influences that are not entirely random, becoming targets or tools for engines like 3i Atlas that appear on shorter, sharper timescales. When you close your eyes, you can picture that halo as a vast, dark classroom, its seats filled with uncounted frozen worlds, most of them silent, a few of them beginning to stir. As you breathe slowly, imagine Bernardinelli-Bernstein back in that classroom, long before we named it, one quiet student among many, waiting on the outer edge. At some point, the forces acting on it summed to a gentle invitation inward. Maybe that invitation was entirely natural, maybe it was subtly shaped. Either way, the result is the same. A giant is on its way, and an engine, 3i Atlas, appears to be moving to meet it. In the next part of this gentle deep dive, we will zoom in from the cloud to the equations that describe how one moving body can catch another, tracing the physics of interception that makes the apparent alignment between 3i Atlas and Bernardinelli-Bernstein not only possible, but disturbingly elegant. When you hear the word interception, it is easy to imagine a last-second swerve, a violent impact caught in a single frame. Orbital interception is almost the opposite. It is slow choreography, planned years in advance, a matter of arranging for two moving bodies to arrive in the same region of space at almost the same time, with a relative speed low enough that they can truly interact. The way you do that is not with drama, but with small, carefully timed changes made long before the meeting itself. The simplest way to picture it is to draw two broad, curved lanes around the sun. To move from one lane to another, you do not leap sideways. You speed up or slow down along your path, trading motion for altitude. A gentle push in one direction lifts the far end of your orbit outward. A push the other way lets you fall inward. In textbooks, this becomes a tidy transfer where a spacecraft leaves one circular orbit, rides an ellipse, and arrives smoothly in another. In reality, orbits are not perfect circles, and burns are not perfect impulses, and targets like Bernardinelli-Bernstein do not sit still. They drift, they are perturbed, they breathe out gas that changes their own motion. Real intercepts are not a single maneuver, they are a continuous calculation. Our own missions have shown how delicate that calculation can be. To meet Comet 67P, the Rosetta spacecraft spent about 10 years weaving through the inner solar system, using planetary flybys and small burns to slowly match the comet's position and speed. By the time it arrived, Rosetta's relative velocity had been trimmed to only a few meters per second, gentle enough for a fragile orbit around a nucleus just a few kilometers across. Cassini's path to Saturn followed another intricate dance, looping past Venus and Earth to borrow momentum instead of spending fuel. In both cases, interception meant accepting that the most important choices were made long before arrival, when tiny course changes had the greatest leverage. From those missions comes a quiet lesson. Fuel is finite. Every meter per second of delta V comes from a tank that will one day be empty. Mission designers learn to lean on gravity and timing, letting the planets do as much of the work as possible. A typical deep space mission might have only a few kilometers per second of total delta V to spend, carefully divided among all burns. A small mistake early can force a large correction later. Interception becomes an exercise in restraint as much as in motion, a discipline of doing just enough, just early enough, and then letting the natural flow of orbits carry you the rest of the way. Now imagine an object that is not limited by tanks in the same way, an engine like the one we have been picturing inside 3I Atlas. Instead of a few sharp burns, it can apply a continuous, very gentle push for years, drawing power from the environment. Mechanically, that is like trading a hammer blow for a steady hand on the shoulder. A millimeter per second of effective acceleration, sustained over months and years, can change a trajectory as much as a brief, violent burn, and often more gracefully. It also allows for fine-tuning. The engine does not have to commit to a single path and hope. It can watch, correct, and watch again, letting the intercept grow more precise as new information about the target arrives. With that in mind, the alignment between 3I Atlas and Bernardinelli-Bernstein begins to look less like a coincidence and more like a solved problem. In the most conservative natural fits, 3I Atlas would have swept through the inner system on a hyperbolic path and vanished into interstellar space, never coming close to where Bernardinelli-Bernstein will be in 2031. The new acceleration changes that. Applied patiently, it plays the role of many tiny braking burns and steering nudges, curling the outbound leg of 3I Atlas back toward the outer system in a way that lines up with the slow arc of Bernardinelli-Bernstein's inward swing. On a computer screen, this lives as differential equations and state vectors. In your mind, you can see it as two pale threads of light that would have missed each other beginning, very slowly, to bend toward the same quiet pool. The real difficulty lies in relative speed. Near perihelion, at a distance of around 10 astronomical units, Bernardinelli-Bernstein moves at only a few kilometers per second. For 3I Atlas to do anything more than flash past, it has to shape its own motion so that, from the comet's point of view, it is almost keeping pace. A brief flyby at tens of kilometers per second would be a momentary glance. A pass at a much lower relative speed, achieved by years of subtle acceleration, would feel more like a visit, long enough for fields, tides, or other interactions to add up. Achieving that kind of almost shared motion between two bodies that started with completely different origins is what makes interception in deep space so demanding. Engineers describe such problems as optimal control tasks. You tell the algorithm where you start, where you wish to end, and what kind of continuous thrust you can produce. It then decides when to push, how hard, and in what direction to achieve the intercept with the least cost. The resulting paths can look odd, full of slow spirals and looping arcs, until you remember that gravity is always tugging in the background. When some analysts look at the reconstructed route of 3I Atlas during its new acceleration phase, what they see is not a wild deviation, but a series of gentle, consistent adjustments that resemble the output of such a planner. 3I Atlas does not lurch. It leans, as if constantly balancing energy, timing, and the quiet limits of a hidden engine. For an object using field-based propulsion instead of chemical rockets, the choices become even more subtle. If 3I Atlas is steering by coupling to the solar wind, redirecting charged particles and modulating how it absorbs and re-emits radiation, then its available thrust changes with distance. Near the Sun, the wind is dense and the light is strong. Farther out, both fade, and the engine must either accept weaker pushes or turn to other tricks. A truly efficient intercept with Bernardinelli-Bernstein would have to account for that gradient, arriving in the outer dark, not exhausted, but still able to trim the final approach. To us, all of this hides behind the simple fact that the path of 3i Atlas bends in just the right way so that, years from now, it will drift into the same cold suburb of space that Bernardinelli-Bernstein is scheduled to cross. Seen in this light, the extraordinary thing about the 3i Atlas trajectory is that the equations behind it are ordinary. They are the same ones our own mission planners use for Rosetta and Cassini. What is different is who appears to be solving them. As you let your thoughts slow, you can set the algebra aside and hold only the image of two long journeys, one from the deep Oort cloud and one from beyond our star, curling toward the same faint rendezvous. The physics of interception says that small, patient forces can always, in principle, make such a meeting happen. The lingering question, which the math cannot answer, is who or what chose to apply those forces in the case of 3i Atlas, and why Bernardinelli-Bernstein was chosen as the place where their paths should finally touch. In the next part of this slow exploration, we will look back to another visitor, Oumuamua, and ask whether its own strange acceleration was an early, quieter rehearsal for the kind of mission that now seems to be unfolding around this larger, darker rendezvous. Long before 3i Atlas began to lean toward Bernardinelli, Bernstein, another stranger, crossed our sky and slipped away before we could do more than whisper about it. In late 2017, survey telescopes in Hawaii found a fast-moving point of light on a path that did not close, already outbound by the time we noticed. It was given a Hawaiian name that meant scout, a messenger from far away, Oumuamua. For a few brief weeks, it sat at the center of attention, painted as a spinning needle or a tumbling shard, and then it was gone, leaving behind a trail of numbers that refused to settle into any comfortable category. Looking back from the era of 3i Atlas and Bernardinelli-Bernstein, that brief episode feels less like an isolated curiosity and more like a first, quiet rehearsal of themes that have now grown much louder. The facts of Oumuamua are straightforward and deeply inconvenient. Its orbit was clearly hyperbolic, so it was not bound to the sun. Its brightness rose and fell with a pattern that suggested an odd shape, perhaps elongated, perhaps flattened, turning end over end as it flew. Most unsettling was a small but definite non-gravitational acceleration, a steady extra push that could not be explained by gravity alone. For an ordinary comet, the escape of gas as ice sublimates would be the natural answer. But Oumuamua showed no obvious coma, no easily visible tail. It behaved like a comet that had hidden its own breath, as if whatever force was nudging it did not want to leave the usual markers on the sky. To keep Oumuamua in the realm of the natural, scientists proposed a chain of delicate models. Perhaps it was made of exotic ices that sublimate invisibly. Perhaps it was a very porous fragment, so light that sunlight could push it more strongly than normal rock. Each model covered part of the behavior, but each came with difficulties. Some required materials that would likely have vanished long before the object reached us. Others demanded fragile structures that would struggle to survive the rough birthplaces where small bodies form. Slowly, a pattern appeared. It was possible to make Oumuamua natural, but only by giving nature a very specific set of unlikely gifts and then having those gifts arrive in our sky at exactly the right moment. Into that gap stepped a more controversial suggestion, one that now feels different in the light of 3I Atlas. A few researchers argued that Oumuamua might not be a random shard at all, but an artificially thin structure, perhaps a light sail riding radiation pressure the way our own proposed solar sails would. In that picture, the non-gravitational acceleration was simply sunlight doing its job, and the lack of a coma was exactly what you would expect from a craft that did not depend on outgassing for thrust. For many, that leap toward an engineered origin felt too large, so the idea was filed away at the edge of respectability. But even as official narratives folded Oumuamua back into strained natural explanations, the question it had raised remained unresolved, floating beneath the surface like a quiet echo. Seen from the vantage of 3I Atlas and Bernardinelli-Bernstein, Oumuamua looks less like a one-time anomaly and more like the first piece of a pattern. Both Oumuamua and 3I Atlas are interstellar visitors. Both show non-gravitational accelerations that visit over time. Both resist the simplest comet story, one through the absence of a coma, the other through the coherence and direction of its new acceleration. The difference is in what happens next. Oumuamua seemed content to pass through, changing speed slightly, and then vanishing into the dark without obviously aiming for anything. 3I Atlas appears to have taken the extra step, using its subtle engine not just to drift, but to shape a path that curves toward the slow inward fall of Bernardinelli-Bernstein. It is as if the first visitor whispered that such maneuvers were possible, and the second arrived to show us what happens when they are used to seek out a specific giant target. A cautious mind will point out that this pattern may live only in our storytelling. It is entirely possible that Oumuamua was a natural fragment with awkward properties, and that 3I Atlas is, despite its new acceleration, another unusually active body. The human mind is very good at connecting distant dots and calling them constellations. Yet even in the most conservative view, Oumuamua changed something real. It proved that interstellar visitors are not rare myths, but actual objects passing through our system. It forced our surveys to become more attentive, and it showed us that when such visitors arrive, they can behave in ways that strain our categories. In that sense, Oumuamua set the stage. It taught our instruments and our institutions what it feels like when the familiar rules do not quite fit an interstellar guest. As your thoughts begin to slow, you can place these three bodies on a single, gentle line in your mind. First, Oumuamua, the fast-moving scout we barely saw, carrying questions we could not yet frame. Then 3I Atlas, lingering longer, carrying a new acceleration that looks more and more like a signature of intent. Ahead of both, Bernardinelli-Bernstein, a giant comet rising inward from the Oort cloud toward its 2031 perihelion, a meeting point that might be nothing more than an accident of gravity, or might be the appointed destination of an engine that has been steering for years. Whether or not these events are truly linked, holding them together like this lets you feel the scale of the story we are living inside. In that wider view, our role looks both small and quietly important. We are not the ones guiding 3I Atlas or choosing the path of Bernardinelli-Bernstein. We may not even be noticed by whatever plans, if any, connect them. But we are the first generation on this planet able to detect interstellar visitors, to measure their odd accelerations, and to ask whether an alignment between a wandering engine and a giant comet is coincidence or design. Past humans watched comets as omens without knowing their orbits. Future humans may look back on Oumuamua and Three Eye Atlas as the first faint hints that our sky is part of a larger, older network of motion. We stand between those two, awake enough to notice and unsure enough to admit that we do not yet understand. So, as this story comes to rest for tonight, you can let the darker possibilities soften at the edges. Picture the solar system as a dim, spacious room. The sun glows at the center. The planets move in their slow, familiar loops. Far beyond them, Bernardinelli-Bernstein glides inward, its ancient ice just beginning to warm. Somewhere along a different curve, Three Eye Atlas leans on its hidden engine, adjusting its trajectory in tiny, patient increments. Far behind, already gone, Oumuamua leaves only a faint scratch on the memory of our instruments. Above all of it, your awareness floats like a quiet observer, allowed to watch, not required to decide. Let your breathing fall into a gentle rhythm, like orbits settling into their paths. Whatever Three Eye Atlas truly is, whatever mission may or may not bind it to Bernardinelli-Bernstein, those answers lie on timescales much longer than a single human night. There will be more data, more debate, more attempts to name what is happening out there. None of that has to be solved in this moment. For now, you can let the question remain open, a soft, distant point of wonder in the sky of your thoughts. As you drift towards sleep, you can imagine the paths of Oumuamua, Three Eye Atlas, and Bernardinelli-Bernstein as three pale threads crossing in a universe far larger than any of them or us. In that vastness, for this small stretch of time, you are safe enough to simply rest and dream. Good night.